Okay, look up. Okay, every class kind of finishes in a different place. So what number did we finish on the gold packet? 11. Okay, look up. Okay, so you're supposed to change your window to 0 to 7, so do that on your calculator. So we turn off acceleration, make sure that's still off. Go to window, 0 to 7, zoom fix. Okay. Okay, key idea. Look. Key idea is you must understand the difference between average versus instantaneous. Okay? Instantaneous, this seems way loud. Instantaneous means like at a given moment. Average means what's happening between two distinct and separate times. They will test you on both. They'll expect you to understand the difference. So instantaneous, the way I memorize it is at an instant. Average means what's happening over time, like from this time to this time. Another way to look at it, Luke, 2 points, is instantaneous is always at 1.1 seconds, like at that instant. Average will always be, well, what happened from time 0 to time 10? Anybody else? Cool. Okay, you have to have memorized this box right here. This box is showing you how velocity and position are related. The whole point of this packet is to get you started on how position and velocity relate to each other, and then how velocity and acceleration relate to each other. The good news is, once you understand how position relates to velocity, there's nothing new to memorize, because velocity relates to acceleration in exactly the same way. So we don't really have to learn two things. We have to learn one thing well, and then you just apply it to a different situation. Questions? Okay. It says on number 12, at time equals 6 seconds, the tangent slope of the position graph. So here's what you should be visualizing. At time equals 6, we'd be here on the graph. Here's 6. And at that moment, here's the kind of marker for that. Tangent slope of position means go to this spot on the position graph and find out how steep the position graph is at that spot. That's what's meant by tangent slope. Like it's a curve, so it has different steepness. You're trying to find the slope at that very spot. That's what they mean by tangent slope. I'm going to show you how you can do that on your calculator, but we have to do a little translation. We're trying to find the slope of the position at a point. The position graph on paper is x of t. Okay? So we're trying to find out the slope of that graph, which means the change in the position divided by the change in time. That's what we're trying to find. We're trying to find it at a specific time of 6 seconds. So we put a bar here and we write t equals 6. That's our goal for item 12. Questions about anything? Okay? We have to translate it to the calculator. On the calculator, the position graph is stored in what's known as Y1 because that's where you put it. Like when you typed in the position formula, you put it in Y1. So on the calculator, you're going to have to type D of Y1. Like that. On the calculator, time is being represented by the x variable. So this will have to be dx. Questions? Cool. And we're doing it again at a time of 6 seconds. So that's what we're going to do on the calculator. Questions? Cool. So grab your calculator. You need to go back to the main screen, which means you hit second quit. Clear that off, so start fresh. Then you type math. Here's the math key in red. And you're going to choose item 8. And then you get that symbol I just drew on the board. So we want the bottom here to be x because x represents time in the calculator. We want the top to be y1 because y1 is the position. To find that in the calculator, you type alpha. And then you hit trace. And then you select y1. I want to do it at time equals 6, and then I press enter. But I need me to show it again. So I go math, then 8. Good to there. This is supposed to be time, but in the calculator, x is time. This is supposed to be position, but in the calculator, position is y1. That list is here, alpha, trace, y1. And then again, time equals 6. Anybody need to see it again? On the Inspire, anyone else have an Inspire besides Spencer? Just Spencer, I'll just come show you then. It's quicker than doing it on the board. So put it flat so I can see it. So you're going to choose that one. And you choose that one. You type in X. Here you're going to hit variable. Choose F1. Put an X inside. Go over. Control equal. Choose the bar. X equal 6. Enter. Function not. Oh, I don't know. Hit escape or something. Go to the graph. Oh, you don't have the formulas entered, yeah. Oh, see, here's the, no, I got it, perfect. So this is why we like to use a document, it's just better. So now go control page, plus page, add calculator, and then the same thing, so yeah, cool. You're welcome. Anybody else? Okay, so back here. So we found that to be, what was it, 155? Okay, again, I say it every day. You can't do what I do, you got to understand what I'm doing. Okay, so when you write down a number 155, don't just write it down, think about what it means. This is telling you that the position of the particle at that moment, the position of the particle wants to be 155 meters to the right of where it is in the next second, because velocity tells you how the position wants to change. It doesn't really change like that because the velocity isn't staying at 155 for an entire second, but that's what it wants to do at that moment. Questions? Cool, next thing. This worksheet seems kind of redundant because I'm trying to get you to see how things are connected to each other. So item 13 says at time equals 6 seconds, what is the velocity of the particle? So go back to your calculator, stay on this screen, and do this. Do alpha, trace, and we want velocity this time. So you choose item 2. We want the velocity at the same time. So you type parenthesis, type 6, type close parenthesis, press enter. And you get the same thing. So the whole point of this idea here is to emphasize that finding the rate at which the position is changing. This is y1. Finding the rate at which the position is changing at time 6 is exactly the same thing as finding the velocity at time 6. They mean the same thing. I don't know. Let me look. Close enough. That's funny. I'm up here like, they're supposed to be exactly the same. So close enough. So. You're okay. You did get 156. That just means one of your formulas is slightly off or something. So let's just check on. No worries. You're fine. That's why, yeah. There we go. No worries. Okay, look up. Oh, please. Oh, quiet. Quiet. It's simply that's where we put the formulas. When you entered into your calculator the formula for position, you specifically took the formula they gave you on the sheet for position. That was the x of t formula. And I had you put that formula into y1 of the calculator. Good with that? And then we put the velocity. Hold on a second. We put the velocity into y2. Get the colors right. You good with that? Did that answer your question? Okay, good job. Anybody else? Hold on, I'm trying to get the name. Shoot. Jonathan Daniels? No, that's not you. Don't move. I'm trying to get your name. It suddenly left me. Ah, shoot. Hold on. Both of your names left me. No, Isaac Irwin, I got his name. This is gone. Tell me your name again. Michael Franson. Don't say it. Yours is, yeah, hold on. Yours is coming. Yeah, that's why it's coming. Julian Wisman. Okay, sorry. All right. Michael, did I answer your question? Okay. Please, Sharon. Close.
Like the relation between those two, like the first one of y1 is saying like what it's going to get to at y2. So then if we're putting in y2 for the first one, and then we put in y2 for the second one, is that the same similar progression on this one?
Yes, let me say it. Okay, I'm going to say back what I think you said. Okay. Everybody look up. Come on, look. There's a couple of things mixed into what Taryn just said that everyone needs to see. Okay, look at the board. It's crucial that you notice that here we found the rate of change of the position. That's 155. Then we found the velocity at that same time. Those are the same thing. And they're going to test you on that. Like, do you understand that they are the same thing? Everybody good there? Your question is right on target. Stay with me. I said that this means the position wants to be 155 meters to the right of where it is. So based on that, kind of makes sense that I could type this. Just watch. I could type y1, and then I could type in times 7. Okay? Oh, wait a minute. We've got to do y1 at 6 first. Hold on. Back up. So let's back this up. Let's do y1 at 6. Okay, this tells me where the particle is located at time 6. So here's where the particle is at time 6. It's way over here on the left. This number is telling me the particle wants to be 155 meters that direction, to the right of where it is in the next 1 second. Questions so far? So quickly on your calculator, what's negative 78 plus 155? Somebody's got 77. Look. So if the prediction is true, that in 1 second my position will be 155 meters to the right of where my position is, negative 78. Right, so I go y1. Dumb, that's good. 7. Come on, brain, work. So 1, and then 7. We would expect 77. Okay? Look, we are not going to get 77. The reason is, this is how fast the position is changing at that exact moment. But it's changing itself. Like, everything's changing, so it doesn't come true because the fact that everything is changing. Not that way. There's another way to predict it we will learn later, but you can't do that. Isaac. It's right here. We're looking at time 6. Isaac sees it, and we are finding a couple of things. Okay, really, like, just keep talking till it really feels good. Okay, look here, look. We found the slope right here. The slope right here, that slope is 155 meters per second. That's also this y value, 155 meters per second, right here. But that's what's happening at that instant. As Isaac said, right after that, the velocity is going up. It's going more and more. So it's like 1 moment later, it's like saying the particle's position is going to change even more. And it just keeps doing that. That's why the particle's position ultimately changed by a lot more. Like it went from negative 78 all the way to 189, which is way more than 155 because that velocity was changing. Did that help answer your question, Taryn? Kind of. You had a different question, right?
Yeah, it was different.
I think your question is the next one I'm going to talk about.
Okay.
Everybody okay? Okay, watch. I said just a moment ago that if you will learn how position is related to velocity, then you don't have to learn anything new when it comes to understanding how velocity is related to acceleration, because the relationship is identical. I think that's what you said. Is that correct? So let's do that. Yeah, so we go to my calculator and I say, let's go find how fast the velocity is changing. It means we would, well, let's leave this here. We go math 8. Time is still x. Now we're going to type y2 because we want to see how fast the velocity is changing. So I choose a 2. Time equals 6 is fine. That's how fast the velocity is changing. But that's the same thing as the acceleration at that moment.
And y3 is 6, all the equal ones.
There we go. So we go y. Is that your question?
Yeah.
Well done, Terrence. Well done. Like that. Yeah, so that's why I say you don't have to learn 2 things. Learn 1 thing. You just apply it to a new situation. So, questions? Please, Rachel. Uh-huh. So what the board is trying to illustrate is this, Taryn, that I'm going to just go through it faster. It'll be easier to see it all together. Is that okay? So here's what we did. We first said, come on. Okay, so we said this first, Rachel. We said, let's find how fast the position is changing. So we went Math 8, and we typed in a Y1 to see how fast the position is changing at time 6. You okay with that? Good. Then we said that's the same thing as the velocity at that time. So we did a Y2, just Y2 itself, nothing else, at that same time. And we expect to get the same number because these two things mean the same thing. This means how fast the position is changing at time 6. This means the velocity at time 6, but those are the same. They're just two different ways of saying the same thing. Is that okay? In fact, here's what I believe. I believe that some hundreds of years ago, they would always say, let's go find how fast the position is changing. That's this one. Let's go find how fast the position is changing. But they did that for a long time, and people got tired of saying, let's go find how fast the position is changing. And they said, let's just give that a name. We'll call it velocity. So when they say go find the velocity at 6, means the same thing. Good so far? And then what we did to extend it is we said, let's go find how fast the velocity is changing. So we went Math 8, and we typed in velocity now to see how fast the velocity is changing. We get that number. Well, that's the same thing as the acceleration at time 6. So we just type Y3, and we put in a 6. And those two values are the same. Is that what you meant? That's a good job, Rachel. 2 points. Anybody else? Awesome. Keep going. So back to here. So we've done this. In answering these questions, we've done all of these things. The velocity is also 155. Okay. That symbol means the same thing as this symbol. Except 4, not 6, but change this to 4. It's right here in the green box. So x prime of 4 means rate of change of position at time equal 4. So you go back to your calculator. Here's a shortcut. You can arrow up if you want. It's not that much shorter, but in fact, in this case, it's probably not shorter at all. You can press enter. You can say, I need this to be y1. So you back up. Alpha trace, y1. I need the time to be 4. There we go. That's the rate of change of the position at time equal 4. Questions? Please. Yep. So that's exactly what the worksheet's going to have you do. So now we do exactly what Kate Crofts, with an S, just said. So we say alpha trace, and now we choose velocity, y2. The time is still 4, like that. Perfect. Questions? And write it in. So. Questions about anything? Please, Rachel. No, that's my error. Thank you, Rachel. 2 points. Yeah, sorry about that. Anybody else? Okay. 15. 15 says, At what time does the particle stop moving left and start moving right? Raise your hand if you know the answer to that. Hands up. Look at your graph. So there's two ways to find it, actually. How do we know when the particle stops moving left and starts moving right? Who knows? So we talked about it last time, but it's just been a while. Long weekend. A few people. Isaac? Of what? I'm going to talk, so that's incorrect, but I want to talk you through it till you can see it. Is that okay? So watch me. Everybody watch. Remember how I said I'm the particle, right? Yeah, hat and all. Okay. So let's see, I don't look up. So here's position 0. Here's position 0. Look at the blue graph. Come on, everybody look. Look at the blue graph. Look at it, what it's doing. Okay, remember, you should be looking at the numbers. The numbers on the blue are becoming more and more negative. Raise your hand, please, and answer this. Does that mean I'm moving left or right? Hands up. If my position's becoming more and more negative, am I moving left or right? John. Left. Who agrees? Point 2 for John. Keep watching. Keep watching. So here I go. My numbers are getting more and more left. Now they're getting less and less left. Right there. So raise your hand if you can tell me, when did the particle change direction? Hands up. Like roughly, when did the particle change direction? When did it stop going left and start moving to the right? Let's go, Lily. So where Lily is looking is right here. Watch. So Lily's looking right here at about x = 5, and that's a pretty good estimate. Right about that time, the values of position stop becoming more and more negative. Wrong button. They stop becoming more and more negative, and they start becoming less and less negative. That's when the particle changes direction. Does that make sense? Question? Harrison? Look up. So here's where Harrison is looking. Okay, focus. He's remembering that when the velocity is negative, you know the particle is moving left. When the velocity switches to positive, the particle will switch and it will start moving right. That's exactly why, if we drew this a little more carefully, these two spots line up. So right there, like that. That is the exact time when the particle stops going left, starts going right. Okay, once again, on a test question, that's the connection you have to understand. They're not going to give you both graphs. I'm giving you both graphs because we're learning the connection. They're going to test to see if you have learned it. So they'll only give you one of the two. So you've got to be able to look at either one and say, oh, I can tell from either graph when the direction changes. That's the idea. Question? Oh, please. Yes, perfect. Yeah, the velocity is the orange, and the blue is position. Nope, perfect. Hold on. Addison. There we go. No, dang. Adeline. No. Shoot. Sudweeks. No, I got the wrong class and everything. I know who you are, but I'm paying now. Marielle Sutton. Sorry, Marielle. It's because an Addison sits here in a different class. So, see, long weekend for me too, apparently. Anybody else? Please. Yes. Perfect. Shh, please. Say it again, Katie.
So, like, I know the blue one. I just think like more of the blue color. Like, how can you tell?
See if this helps. Right here, right there, you should be thinking of the number. Is that number represented by that orange dot positive or negative? How about that orange dot? Yes. Did that answer your question? Good work. Please.
So like on a test, would it give you like the velocity graph and then it would ask you like other questions on what it would be on the position graph if
Hmm.
you don't have it?
Yes. Yeah, it's what. Don't say it. Maddie. Look at me. Look. That's exactly the idea. Is that can you look at one graph and answer questions about the other? Yep. And vice versa. One thing about the points. Really, the whole idea is just to get people participating. So if you raise your hand and you ask a question or clarify or anything or answer a question, and I forget to say your name or I forget to say point, always mark it down. Like every single time, mark it down. If I want to give you more points because whatever, just for randomness or just because it was a little better comment or question, I'll specifically say 2 or something, but always mark it down. Like interaction is how you get paid. So questions. Cool. Keep going. So we know the particle. Oh, we got to find that time. So go to your calculator. Go hit graph. Choose second trace. You notice we use the trace key heavily. That's kind of nice that it's always the same key. You're going to choose 0, number 2. We want to find the 0 of the velocity because we're looking for this spot right here. That's where the velocity is 0. That's why it's called the 0. So move your cursor to the velocity graph. You know it's there when it says y2 up here. Now we know we're in the right spot. The calculator is asking you a question. It says left bound. Okay, it says left bound. That means you need the cursor on the left side of the 0. Right now the cursor is on the left side, so you're fine. You just press enter. Now the question changes. The question says right bound. So you must move your cursor to the right side of the 0's location. Something like that. Press enter. Now the question changes to guess. Guess means please put the cursor near the location of the 0. Press enter. Okay, your calculator must say 0 or you did something wrong. So make sure it says 0. Please. No worries. So the key idea is this, Kate. First thing, of course, is to understand what the heck I'm trying to find. You with me? So I know that I want to figure out this spot right here. Like, what is the time when that velocity is 0? So when I go to my calculator, I first say I want to do second, trace, and I want to choose 0. Good? Okay. Once I make that choice, now I've got to put my cursor on the correct graph. So I want to make sure I'm on y2 because that's velocity. So I move the cursor to y2. You good there? Okay. The question says left bound. That means, Kate, I must move my cursor to the left side like that. Press enter. Good there? I'm messing up. Do you go by Kate or Katie? Kate. So I'm doing it okay. Okay. Now it says right bound. That means move your cursor to the right side of the 0. So the 0 is right here. So my cursor is now on the right side. Press enter. Good. Okay, it says guess. That means move the cursor to where the 0 is located, approximately. Good enough. Press enter. And make sure your calculator says the word 0. Did it work? Good job. 2 points. Anybody else? Please. I'm not sure either. I don't do the Inspire very much. Sorry, odd man out. Go escape. choose analyze. Choose 0. See, it says graphs. It wants you to choose the graph you're going to do it to. It says lower bound, so it wants you to go to the left. I think you can actually cursor over there and click. There we go. No, to the left. There you go. That's great. It doesn't have to be very close. So that was now you're doing the upper. Enter again. And there it is. 4.8. We just need to change your settings. You need 3 decimals. So you'll have to go into like the settings and change that. But, okay. Okay, back to the sheet. Okay, right on your paper it says, at what time does the particle stop moving left and start moving right? That was 4.848 seconds. Okay, look. 1 second, Isaac. Hey, look. Okay, a good score on the AP test is very associated with good habits. So here's a habit you want to develop today. Don't ever write a number without assigning it to something. Like the AP test writers are going to expect you to communicate with them, not just hand them a pile of numbers. So you write T for time. Time equal 4.848. And then make sure you have units. That also is often given points. Please, Isaac, go ahead. Gotcha. So are you okay, Isaac, that looking at the graph, we can identify that we want to find this spot here, yes? Good. So we go back to our calculator. 2 points for Isaac. We say second, calculate, and now we're going to choose minimum. 3. And now it's basically the same thing again. Make sure you're on the right graph. We want to be on Y1. It says left bound, so I go left a little bit. Enter, right bound. Go right a little bit, enter, guess. Kind of put it where it is. And then again, make sure it says the word minimum. Good question. Anybody else? Oh, please. Let me look. Question. Hold on. So get quit. Just hit enter. Graph. So do it again. Oh, stop. So here's what you did wrong. Go second, trace. You chose 0, but you were actually then working with the minimum. I think, maybe not. I don't know. Which one are you looking for? Yeah, Yeah, the blue. That was the problem. So hit graph. Hit second, trace. On the blue, we're looking for the minimum, the low spot, not the 0. Okay. Do you understand the difference? Okay, yeah. Anybody else? Okay, we talked about, so we did it together. We found the time when the particle stops moving left and starts moving right. We also talked about how to find that using either velocity or position. So we've covered item 15. Question. Cool, next thing. Item 16. So now they want you to turn the acceleration back on. And so just go to y equal. Turn it on and zoom fits. Are you okay to question for my uncertainty about her preferred name there? So, oh, you have a ticket then, sorry. Pretty much do everything I can think of to get you to raise your hand, so you don't have to pay for anything. Questions? Cool. Okay, so we've got it all turned on. Come back to here. I've said this a couple of times today already. We've talked about it already. If we're good on how position relates to velocity, no big deal to see how velocity relates to acceleration. You'll notice this box here in purple looks exactly, like the other box we saw when we were relating position and velocity. Questions? Please, Michael. What's that? Oh, let me come look, Michael. Oh, Zoom. Oh, did we not change it? Oh, I got you. Yeah, it changed back. You're right. Yeah, this has gone back to 0 to 1. Sorry. So this is 0 to 1. I don't know. Didn't really tell us, did it? You should go 0 to 1. My bad. Sorry. So if I go 0 to 1 now, and then zoom fit, that's the packet didn't really say that. My bad. Is that the problem, Michael? Okay. Anybody else? Please, Maddie.
So you know how like velocity is negative and it's moving left? Is that the same? Does that apply to acceleration also? So if it's like the acceleration is negative, then it's moving left.
No, no. Hey, look up. Listen, listen, listen. Okay, I want to talk through Maddie's question, see if this will click for everyone. Okay, I'm the particle again. I'm standing here in the center of the room. Okay, if my position is becoming more and more negative, that means my velocity is negative because velocity tells me how the position will change. So velocity is saying, I want your position to be more negative. So velocity being negative means positions, particles moving to the left. Acceleration tells me how the velocity changes. So let's write some things down here. So let's say, okay, now I'm giving a really simple example. We won't typically be tested on something this simple, but it helps understand the idea, and then you can apply it to more complex situations. If you had a position, let's build a table here quick. This is Maddie's question, I believe. So here's time. Here's position. It's the blue. It's not this blue, but whatever. Okay, we said that at time 0, the position was 0. Okay, velocity tells me how the position will change. So if we have a velocity that's never changing, the velocity is always going to be, we'll say, -3 meters per second. That means the position wants to change 3 meters negatively every second. So using that information, if this truly were constant, this is back to Taryn's question, you could accurately predict the new position. So raise your hand if you can tell me, if my velocity is always -3 meters per second, what's my new position going to be 4 seconds from now? If my current position is 0, what's my new position, raise your hand, going to be 4 seconds from now? This is what velocity means. Haley Pedroza. So Haley says -12. That would be meters. Raise your hand if you agree. 0.2 for Haley. Does that make sense, Maddie? Okay. Now, what the other relationship that you're talking about is this one. Here's time. Here's my velocity. Let's say the situation is that at time 0, the velocity is, let's say, 12 meters per second. Well, if the acceleration is constant, we'll say the acceleration is, I don't know, we'll say -5 meters per second every second. Okay, that's telling us how the velocity will change. So in exactly the same way that the velocity tells us how the position will change over some time period, the acceleration, if it were constant, that will tell us how the velocity is going to change over some time period. So that's how those things are connected. You don't look at acceleration and say, well, how is the position going to change per se? That's harder to think of. You say, no, acceleration tells me how velocity changes. So raise your hand if you can tell me, what would the new velocity be? We'll say, we'll start easy. We'll say in 2 seconds. What is the new velocity in 2 seconds? The acceleration tells you how the velocity is going to change. This says how my velocity is going to change every second. So what's my new velocity at time 2? Hands up. Hannah? So, right idea, you just went the wrong direction. No worries. Like, stay with me. If this had been a positive 5, your answer would have been perfectly correct, because the velocity would have gone up by 5 meters per second every second. Because it's negative, it went the other way. So instead of being 12, 2 seconds later, it's Chris, 2. 2 points for Hannah, 2 for Chris. Raise your hand if you knew it before it was said. Point. Question. Did that answer your question, Maddie? Okay. Anybody else? Awesome. Okay, just got to write some stuff down here now. It says velocity at time 0. So we can go back to our calculator. We can do it here. We can do it from the main screen, whatever. Come on. There we dumb board. Second, quit. So we want the velocity at time 0. So I go y2 times 0, -1. We already talked about that symbol represents how fast the position is changing at time 0. Questions? Like it's saying the position wants to, change by that amount. It says at time equals 0 seconds, is the velocity increasing or decreasing? Okay, warning. Warning. Don't mix up positive and negative with increasing and decreasing. They are different things. Look at this graph. Just say it as a chorus. Right here, the orange, right there, is the velocity positive or negative? Say it. Negative. As I move along the curve, the velocity is going up. Okay, when you see a graph that is going up, that means increasing. So at this moment, right here, the velocity is negative, but it is increasing. It's getting less negative. So the velocity is increasing. How do you know? Because you can see the graph going up. So, questions? Please, Harrison. No, we'll talk about that soon, but not quite yet. So, yeah, the acceleration really can't. Well, you're asking, can I use the acceleration to tell? Say it again. Don't say the foul language, but so can I use acceleration to tell if what? The velocity is increasing or decreasing? Yes, that you can do. I may have heard wrong the first time. You can definitely do that because, again, if the acceleration is positive 3 meters per second every second, that means the velocity wants to go up. by 3 meters per second every second. So this positive velocity tells you, this positive acceleration tells you that the velocity is definitely increasing. You can see it here. Say it out loud, please. Is the velocity increasing or decreasing? Say it. Increasing. It's still going up. It's a little hard to see. It stops going up right there at exactly the same moment when the acceleration ceases to be positive. When the acceleration becomes negative, it's going to make the velocity go down, because the acceleration tells me how velocity changes. What you asked? 2 points. Please, Luke.
So even though the velocity is increasing, the position is still
Right, and here's why. 2 for Luke. My velocity is, and this is exactly what they're asking you to figure out. My velocity is negative, so I'm moving left. But as I move left, this sounds weird, my acceleration is positive. That means my velocity wants to increase, which means my velocity has to get less negative. Less negative means I am slowing as I move to the left. So I'm still going to the left. That's why the position graph is all negative, because I'm going to the left. But as I move to the left, I'm slowing. That's because the acceleration is making the velocity less negative. Eventually, but then right here, the velocity becomes negative. That's making the velocity, the acceleration becomes negative. That's making the velocity more negative. That means I speed up. So I go faster and faster to the left. I don't know if that helped at all. That was a really bad explanation, but kind of.
I understand the I don't understand the acceleration. I understand obviously like the distance and then the velocity. I understand the
Okay.
acceleration.
Let's try this, Luke. So right here, everybody together. Say velocity right here. Everybody together. Positive or negative? Say it. One more time. Velocity, positive or negative? Say it. Negative. At that exact same moment, acceleration, positive or negative? Say it. Positive. Okay, now I'll say it back to you. Look. The velocity is negative, so I'm going left. Acceleration tells me how velocity wants to change. So the acceleration is positive, so it wants the negative velocity to become more positive, less negative. Does that make sense? But a less negative velocity means I am slowing as I go to the left. That's why right here, right there, that's what's happening. All of these accelerations are positive. So they're all telling the velocity become more positive, less negative. The velocity is getting less and less negative. It just never gets to zero. So the particle never goes to the right. It just gets to this moment right there. The acceleration is zero. The velocity is still negative. The particle is still going left. Then the acceleration becomes negative. That's telling the velocity you need to get more negative. So that's why this graph here in orange is going down. Those values are getting more and more negative as this thing is getting, like as long as this is negative, this has to go down. Because acceleration tells the velocity how to change. The red tells the orange how to change. The red is saying, this negative number says this has got to become more negative. It's hard. We'll talk about it more and more and more. We'll get it, but oh, very good. So that was helpful then. Anybody else? Question, Luke, still? Rachel, go ahead.
So, like, if the acceleration graph is, like, really negative, does that mean that the velocity graph is becoming more negative faster?
Look here. Look. You guys really are just dead on target. Like you're going exactly where you need to go, because you're not just doing what I'm doing. You're thinking through it. Listen to what Rachel said. She said, if I heard right, if the acceleration is very negative, that means the velocity graph's got to be steeper, because it's got to be going down quicker. That's because the y-coordinates of the red graph, those y values, each one of those is a slope of the orange. So the more negative the y value is on the red, the steeper the slope of the orange. That's what slope means. Slope means rate of change. So exactly what Rachel said. This negative number on red is going to tell you how steep the orange will be. The more negative the red, the steeper the orange. It's easier to see. Go to your calculator. Hit window. Go 0.6. Zoom fit. It's easier to see on the bigger graph when they're all interacting together. You can see exactly what Rachel's talking about. Watch the red. Notice how the red, yeah, in fact, you can see it right here. The red is becoming, well, let me wait. Hold on. Come on. So the red was becoming more and more negative. That was causing the orange to go down faster. Right in here, the orange is trying to go down faster as the red's getting more and more negative. About here, the red stops getting more and more negative. That means the orange stops going down faster and starts to level off. Exactly right. It's perfect. Anybody else? Please. Oh, no. Please, Isaac. So I'll get you to answer it. So through here, the velocity is negative, velocity is still negative, velocity is still negative, right? So that means the particle is going which direction? Left. That means the position values, the y-coordinates of position, must be becoming more and more negative because I'm moving further and further left. And they are. All these blue dots have a value that's more and more negative. Here the velocity, ooh, come back. Okay, here the velocity stops getting more and more negative. Still going left though, and it's starting to become less and less negative. So I'm still going left, but I'm slowing as I go left. Still going left. Right, because I still have to be going left with my position graph. 2 points. Yes. There we go. Right here, hey, we talked about it already, 2 points for Taryn. Right here is the exact moment when my velocity switches from negative to positive. So exactly that moment, I start coming this direction. But my position is still negative because I'm way over there. But now my position, yeah, Soraya sees it. Now my position is, shoot. So exciting. So, right here, oh boy, right here, Soraya sees that my position is way over there, but because I'm going to the right, my position is becoming less and less negative. Does that make sense? 2 points for Soraya as well for being a good sport. Anybody else? Awesome. Cool. Okay, so back to here. It says, what is the acceleration of the particle at t equals 0? You can just find that on your calculator very quickly. So we go here. We can do the trace thing, or we can go to the main screen. Either way, let's go to the main screen. It's a little easier to remember what we're doing. Clear. So we go alpha, trace. We choose acceleration, which is 3. And we want to find out what's happening at time 0. Is that what it said? So like that. So 8. Please, Luke. So here's how you remember. Everybody, look. Watch. Okay, memorize this pattern, and then the units will always help you. They won't hurt you. In this problem, we're measuring position in meters. Like where I'm located in meters. Velocity tells me how fast the position wants to change. How fast the position wants to change. Therefore, it is measured in meters every second. How fast this wants to change every second. Acceleration says, how fast does the velocity want to change every second? So it's measured in meters per second every second. Because it's telling me how fast this wants to change every second. Anybody else? That help? Cool. Okay, this is, what was it, 8? Oh, I did the wrong thing. This is -1, yes? I was messed up there, sorry. Yeah, my bad, sorry. We've done, the t equals 0 second, velocity is increasing, we already did that. The acceleration is 8 at 0 second. Oh, okay, this is confusing. My bad, I apologize. We're getting there. My bad, my bad. What they want you to put on 19 is this. The acceleration is positive. Sorry, that's my mistake. At time equals 0. So the velocity is increasing at that time. That's what they want. Questions? Okay, v of 0, we already know that's -1. V of 1, I think we did it earlier, it's -10. Is that right? I think it's like earlier in the worksheet we did it once. We can do it again fast, just type it in. 2 point, there we go. Like so. Good. Questions? It asks for the change in the, oh, raise your hand, please. What goes here? Just make sure you're thinking with me. Hands up. What goes here in this blank? Hands up. What goes right here on this purple line? Hands up. What goes there, Riley? The velocity went from -1 to -10. Therefore, the velocity changed by -9. How many knew it? 0.2 for Riley. Questions? Okay, so I think I said earlier today that one key thing you've got to keep track of is, okay, we've been having a really good discussion of difference between position, velocity, acceleration. You also got to keep track of difference between instantaneous and average. With me? Okay. This right here is average. It's saying how much the velocity changed from one time to another. So by what amount does the velocity change? It changes by -9 meters per second. And it does that over 1 second. So this is Luke's question again. That right there would be average acceleration. It's how the velocity changes from one time to another. That's average acceleration. Questions? Cool. Let's go to the next item here. Here they talk about that. It's simple. It's just right here, average acceleration. So I just did it. The average acceleration for that time period is -9 meters per second for 1 second. Acceleration tells me how velocity wants to change. That's how the velocity changed for that 1 second time period. Questions? Okay. Therefore, on average, the velocity is, this should say velocity, sorry. Your worksheet, I believe, says velocity there, item 23. Okay, so I just need to fix the screenshot. So therefore, on average, the particle's velocity is changing by -9 meters per second every 1 second. Question? Please. That's average acceleration because acceleration simply means how the velocity is changing. Yep, that makes sense. 2 points. Spencer. Anybody else? Okay, cool. Next thing. We're supposed to change our window to 0.7, so just hit window. Zoom fit 0.7 here. Questions from anyone? Awesome. Let that plot Very exciting. My calculator on the board, for some reason, I have a full PC computer and it's the slowest calculator in the room. So crazy. Okay, back to here. So next one. This is, back to Spencer's comment, this now is talking about instantaneous acceleration. And we did this earlier today, so you guys have a big head start on this. At t equals 6 seconds, the tangent slope of the velocity graph is what? So we can go find the slope of the velocity, which means we would be right here. This is at what time? Once it at 6 seconds. So we'd be right here, finding the slope right there. The slope right there, this is what Rachel talked about as well. That slope must be this y-coordinate. You'll hear me say that over and over again for many days in the future. This y-coordinate is this slope. So the y-coordinate of the acceleration is the slope of the velocity. That you have to memorize that connection. So here it says, what is the slope of the velocity? We just go to the main screen, second quit. To find the slope, we hit Math 8. So we go Math 8, put an X, alpha, we want velocity this time. We want it at time 6. That's the slope of the velocity at time 6. We write that in. The acceleration has to be the same thing, but it is a good idea to just check it to make sure you're understanding properly here. We do a 3 at time 6. Sure enough. Questions about anything?
So you said the y-coordinate of the slope of velocity?
I said it badly. Let me say it back to you. The y-coordinate of acceleration is the slope of the velocity. Therefore, the y-coordinate of the velocity is the slope of the position. Does that make sense? Do it right here, Taryn. It helps. Look at this picture and notice right here, this is the position graph. Is the slope of this position graph at this spot positive or negative? Positive. Therefore, the y-coordinate of the velocity must be positive, because this y value is the same as this slope. So it helps to point. The words get so many, but is that you good? Okay. Anybody else? Awesome. V prime of 4. V prime of 4 means rate of change of velocity, so slope of the velocity. So back to here again. Slope of the velocity means Math 8. Slope of the velocity, that's y2. Time is 4 now. 32. So that means the value of my acceleration at that exact same time must also be 32. Questions about anything? Really, big ideas are instantaneous versus average, and then just how position relates to velocity, how velocity relates to acceleration. So, okay, that's it for the gold, yes? Yeah. Okay, listen, look up. So we're done with this now. I will ask, because some people aren't here, like when I see you in class on Thursday, I'll say, hey, did you finish the gold? You've all finished it, but I'll be paying for this. And then what you do at home is the green. It should go very quickly. Again, I did not give the hour and a half to 2.5 hour thing in the disclosure to frighten people. There will be assignments that take longer, but don't try to make them all that long necessarily. So the green is the homework. So have that done by the time you come to class on Thursday. And you can get started on the green. We don't usually have time to do this, but go ahead and jump in. We have a few minutes, so. I think there's 3 of them there. Hand one to Harrison. I think there's 3. Hand one to Haley. If there's, yeah, there we go. I think there's 3 there. Hand one down to Hannah. The test is 25 questions. Every question is multiple choice. And every question is all or nothing, like either get it or you don't. So. There's an extra. Give one to Kate. There's 2, I think. So you and Caitlin.